Hi everyone, welcome back. We'll get started again. In this particular video, we're going to start talking about stereoisomerism in more detail. And in fact, we will focus on one aspect or the key aspect of stereoisomerism for molecules, and that's the concept of chirality. Okay, so that's how this word is pronounced, chirality. And so what we're going to talk about here is we will talk about chiral or achiral objects, molecules, achiral and chiral. What do these terms mean? Okay. Now, to keep it very simple, the term chirality or chiral, achiral, these don't necessarily have anything to do with like molecules, okay? Because these can apply to objects in general. So a chiral, an achiral object, okay, an achiral object or a molecule, when we go into molecules, but we'll start with objects first, okay? An achiral object is something that is superimposable on its mirror image, okay? So an object that's superimposable or a molecule, okay, when we go to a molecule. So the key here is superimposable on its mirror image. Let's see what that means, okay? And for the lack of resources here, I have two pens, okay, that I found in my office. Ignore the ink content in these pens, okay? But let's say if I take one of these pens, and I'm going to ignore the inscription here, okay, the labels on these pens, I'm going to ignore those. But let's say if these are just two pens, and if I take this pen and I hold it in front of a mirror, the mirror is here, okay? So orthogonal to me, that's where the mirror is. There's a mirror right here. And if I hold this pen in front of the mirror, I should see this. It's mirror image. And again, like I said, ignore the ink content, okay? The ink level in these pens, because that's clearly different and they don't look like mirror images for that reason. But if we ignore the ink content, if I hold this object in front of a mirror, an imaginary mirror here, I'm going to see its mirror image. And now I can take this mirror image and it can basically overlay, okay? In principle, if I wanted to, I could just overlay that mirror image, the mirror image, on the object itself. So superimposable means overlaying. Now, a complete overlay, okay? So superimposable means overlay, okay, on that object. So for that reason, what I can say is that this pen, if we ignore the label and ignore the ink levels, these two pens are achiral objects, or this pen is a achiral object, actually not these two pens, because the other one was its mirror image. So because this pen has a mirror image which can be superimposed on this object, this is an achiral object, okay? And the same applies to like other objects. I found another set here of objects which would be achiral, my safety glasses, okay? So if I hold this safety glass, and again, I'm going to ignore the label on the safety glass itself, okay? But if I hold this safety glass in front of a mirror, again, an imaginary mirror here, okay? And think about its mirror image, I think I'm going to see another safety glass here, okay? And now I can take the mirror image and superimpose on or overlay on the object itself. I'm not going to force it because I don't want to break my safety glasses, but these are superimposable. The object and its mirror image, they can be superimposed. So what that means is this safety glass without its label is going to be an achiral object. This is achiral, okay? This is achiral. So that's what achiral means. And this concept of chirality basically deals with the superimposability or the non-superimposability on mirror images, okay? So chiral objects, on the other hand, these are non-superimposable, or what that means is do not overlay on its mirror image. Okay, so these do not overlay on their mirror images. So now I can bring these pens back. And now if I include the labeling or maybe the ink levels, right? Well, the ink levels is different, clearly different. But if I include the labeling, notice how if I hold this molecule or this object in front of a mirror, again, an imaginary mirror here, when I hold this object here, well, this is not its mirror image, clearly. Okay, so that doesn't work because they do not give us the mirror images. But our hands, they are chiral objects, because if I hold my hand, assuming again I have perfect symmetric hands, okay, if I hold my left hand in front of a mirror, I should see my right hand. These are mirror images of each other, but I cannot superimpose these, okay? I cannot overlay my right hand or my left hand on the other hand. That means these two mirror images are non-superimposable, okay? These are non-superimposable. And so that means my hand is a chiral object because it does not superimpose or overlay on its mirror image. Now, you might wonder, okay, why don't I do this? Because these overlay. Not really, because when I take my object and its mirror image and I'm trying to overlay, we're talking about like a complete superimposable, not just like laying them on top of each other. So these would not overlay because my palm is going to would have to like overlay with my skin here for it to be a complete match, and that does not happen. So for that reason, when we do this, that is not considered superimposable, okay, because there isn't like a complete match. Okay, so chiral objects, and I'm sure you can find like other things. So for example, like the inside of a car. If you imagine a car, I mean, just the outside, chances are if you get to whatever that might be, like Tesla, whatever that might be, like Model S, models, whatever that is, right? If you take two cars, just the exteriors, same color and everything, they should look like mirror images of each other. So they would be achiral objects. But if I also consider the interior, because let's say the driver's seat, if it is on the left-hand side in the object, then its mirror image, that driver's seat, is going to be on the right-hand side. That means they will not superimpose. Okay, so that would be another example of a chiral object. So chirality as a term, like I said, it only has to do with superimposable or non-superimposable nature of an object and its mirror image. Okay. Now, when, like I said, when an object or a molecule is non-superimposable on its mirror image, then we call it chiral. But when we talk about molecules now, okay, so let's say molecular chirality. That means chirality in molecules. How would we do it? Like, how can we take a molecule and then always like consider its mirror image and then test overlap and things like that? I mean, that is a little bit difficult, but that is how you do it. You still look at non-superimposable nature. And then that is like the easiest way to tell molecules apart. If if two molecules are mirror image, if there are two molecules that are mirror images of each other and they do not superimpose, then they will be chiral. And we'll look at like some of these examples later. But What we're going to do here is we will focus again, like I said, on sp3 hybrid carbon atoms. Okay, and we will try to see, okay, what would make a molecule chiral, or when would a molecule become chiral if it has an sp3 hybridized carbon atom in it. Okay, now if a molecule has four of the same groups, okay, then you can maybe make a model and convince yourselves that that molecule is going to be an achiral object. That means it will be superimposable on its mirror image. Okay, and now this topic is different. Okay, we're not talking about something related to achiral nature here. We're talking about molecular chirality in general. So let's imagine a molecule which has three identical groups connected to it. Now, actually, when I say a molecule, I'm referring to a carbon, an sp3 hybridized carbon here, which has three identical groups connected to it, the three black bonds, and there is one group that's different. Okay, if I take this molecule and if I place it in front of a mirror, again, the mirror is here. If I hold it in front of a mirror, now I do notice that my bond here is slightly different, but ignore that, okay? I think I should see this, okay? Let me do it like this so that everything is the same. So I should see this. And these two molecules, they are mirror images of each other. Notice how these two are pointing at each other, the blues are pointing up, and then the two blacks are pointing away, okay? So these are just mirror images of each other. Now, if I take the mirror image and I try to bring it closer to the molecule, the object itself, they do not superimpose, but I can rotate, and what I notice is that now they are superimposable, okay? All the groups can overlay with the groups on the object. All the groups in the mirror image, they overlay with the groups in the object. So that would mean that when a carbon has three identical groups on it, okay, when an sp3 hybridized carbon has three identical groups on it, then that molecule, or that center where the carbon has four different groups, that is an achiral center, okay? This is an achiral center because this carbon lets the object and the mirror image overlap. Okay, let's move on. Let's go to a molecule where there are only two identical groups. Okay, so there are two identical groups. The other two groups are different. So we have yellow and red, and then the two blacks. If I place this molecule in front of a mirror, if I hold this molecule in front of a mirror, I'm going to see this, okay? It's mirror image. Now, would this make like two different groups? Okay, two different groups. Would that make this molecule chiral? Let's test that out. So I take the mirror image and I take it closer to the object itself. And what I notice is, okay. And as I turn things around, looks like they would come and overlap again. So the molecule, the object or the molecule and its mirror image, they overlay on each other. They are superimposable. So that means when a carbon has two identical groups connected to it, or if you think about only two different groups on it, then the carbon is also achiral, okay? Then that molecule and the carbon would be achiral, okay? Because there's superimposability. Now, the next step up is when we have four different groups connected to a carbon atom, okay? So this is a molecule where we have four different groups connected to that carbon. If I place this in front of a mirror, okay, I will get its mirror image. That's this molecule, okay? So notice how we have yellow, red, black, and purple, okay? And if I take the mirror image and bring it closer to this object, and then I try to rotate, I can move around things, what you notice is two of the groups would superimpose. Okay, the yellow and the red superimpose, but the black and the purple do not. Now you can turn these things around as much as you want. You can always get two groups to superimpose. So I can get the black and the purple to superimpose, but the yellow and the red would not match. They would not overlap with each other. And so what that means is when we have a carbon atom, an sp3 hybridized carbon center with four different groups connected to it, then this carbon now is chiral, okay? Or the groups about this carbon are chiral. That molecule could be chiral. Now we'll talk about this more. Okay. Now, this carbon, which has four different groups connected to it, is called the chiral center or a chirality center or an asymmetric center. There are like different names to it, but I think the simplest one is just chiral center or chirality center. Okay, so this carbon is called a chiral center, a carbon which has four different groups connected to it, because when you have that situation, now you've generated chiral molecules. Okay, you will get a molecule that's chiral. Okay, so hopefully using the models, I was able to convince you that molecular chirality, okay, this arises when four different groups are connected to a carbon atom. Now, it does not have to be carbon. Honestly, we are talking about organic compounds. That's what it's referring to, carbon, but it could be nitrogen, it could be phosphorus, it could be any other element, okay? When it has four different groups connected to it, then key here is we are talking about tetrahedral geometry, okay? To keep things simple again, then we will get molecular chirality. The molecule becomes chiral. Okay, this will give us chiral. This will give us chirality, although not always true. Again, we'll look at some exceptions, okay, where it is not entirely true. Okay, that the presence of such a carbon does not guarantee chirality. Okay, because there are molecules which contain chiral centers. Now, this is especially true when you have more than one chiral center. If there is only one chiral center in your molecule, then the molecule is for sure going to be chiral. But when you have more than one chiral centers in your molecule, then you may, or the molecule may or may not be chiral. Okay, so there are reasons for that which we'll go into. Okay, and the carbon, or like I said, this is more generalizable atom, which is connected to four different groups, is called a chiral center. Okay, that's called a chiral center. And like I said, there are different names. It is sometimes called a chirality center, an asymmetric center, an asymmetry center, things like that. Okay. Asymmetry center, that's like another name. These are all names for a carbon which is connected to four different groups. Another atom, it could be another atom that's connected to four different groups. Okay, so let's look at some examples of this. What would be like an example of a molecule where you're going to see chirality? Okay, let's say we have a carbon, and I'm going to start drawing some loose structures first, but then we'll go to bond line structures. Okay, so let's say we have a carbon with a fluorine, a hydrogen, a chlorine, and a bromine connected to it. if you can imagine a molecule like that. Okay, so we have fluorine, hydrogen, chlorine, and bromine. So notice how there are 4 different groups connected to the carbon. So in this particular case, this is a chiral center. And chiral centers are represented by a star, okay, for the purposes of this chapter, okay, or in organic chemistry in general, if you see a star on a carbon atom or around a center, that usually represents that is a chiral center. If you're trying to identify chiral centers, okay, that's what we're trying to do. Now, for a molecule like this, if I have to draw its mirror image, I think what I like to do is I always like to imagine a mirror plane that's like orthogonal or perpendicular to the plane of the board here. So we can draw the mirror image. So if this molecule is in the mirror image, or if you're seeing this in the mirror, I would think hydrogen is here. It would go up to the carbon. The fluorine is going to be there. The chlorine is on a wedge, so it would go there. And then the bromine is going to be on the dash. Okay, that would be its mirror image. And these 2 molecules, okay, and we'll go over this in detail later, okay. So molecules that are related to each other as non-superimposable mirror images are called, there is a special name for them, enantiomers, okay? And enantiomers are one kind of stereoisomers. Okay, so these are enantiomers because what we know, what we've seen before is when a carbon has 4 different groups to it, connected to it, then it will be non-superimposable on its mirror image. So this is a molecule, that's its mirror image. Because there is a chiral center in this molecule, these must be non-superimposable on each other. And for that reason, these 2 are enantiomers of each other. That's the relationship, okay? So the relationship here for these 2 molecules that we've drawn, that relationship is enantiomers. Okay. Okay, now that's just one example. Let me draw another example of a molecule that could be chiral, and we'll draw it in like bond line structure so that we can again see if we have like a chiral center, you know how to identify chiral center. So let's say we have a molecule like that, and there is a bromine here, let's say on a wedge. Now, if you notice that this molecule, there are several carbons in this molecule, and I will highly encourage you to actually go through this exercise and do it. There are several carbons in this molecule, but this carbon here, I'm going to say that's a chiral center because this carbon here is connected to a methyl group. It is connected to an ethyl group, and there's a bromine and a hydrogen, which is on the dash, right? So there are 4 different groups connected to this molecule that would make this a chiral center. Now, again, I just want to show you how I would draw the mirror image, okay? Methyl would be here, go up, go down to the ethyl there, and then the bromine is going to be on the wedge here, and the hydrogen is there. Okay, that would be its mirror image. These have a carbon which has 4 different groups connected to it. That means it's a chiral center. And so these 2 molecules would again be enantiomers of each other. Okay, those would be enantiomers of each other. Now, let us quickly look at maybe a molecule which would have chiral centers, but it would have chiral centers, but the molecule itself is going to be achiral. Okay, let's look at cyclohexane, let's say. On this cyclohexane, let's say there's a methyl group there, a hydrogen here, methyl group there, and a hydrogen here. Okay. Now, again, I would encourage you to work this out. Okay. Identify that there are 4 different groups. I think these are both chiral centers, because if you look at this carbon, this has a hydrogen connected to it. It has a methyl group connected to it. Those are 2 different groups. Then on to the left, there is a CH2, okay, carbon with 2 hydrogens connected to it. And then another carbon. That carbon is connected to 2 hydrogens and another carbon. On the right-hand side here, this carbon is connected to 1 hydrogen and then 2 carbon-containing groups. So that means they're different, so they're achiral. So this molecule has 2 chiral centers in it. But if I imagine its mirror image, okay, which is going to be this molecule here, okay. These 2 mirror images, what do you guys think? Are they superimposable or non-superimposable? I would say they are superimposable, because if I take this molecule out and then put it on there, they would overlap. Okay, so these would be superimposable on each other, which means this set here, this is achiral. In fact, there is no set here. Okay, I said set, but there's no chiral. When you have an achiral molecule, okay, these are superimposable. And we tried drawing a mirror image, but these are superimposable. And hence, since they are superimposable, they are the same molecule. There is no difference between them, because one can be superimposed on the other one. Okay, so there's no difference. So that's an example of a molecule which has chiral centers in it, but it is achiral. Now, it turns out for molecules, objects like this, when an object is achiral or when a molecule is chiral, the reason is, okay, the reason is an internal plane of symmetry. Okay, internal plane of symmetry makes molecules or objects achiral. Okay, that is the reason why the molecule is achiral. Now, what does the internal plane of symmetry means? It is a mirror plane. Imagine a mirror basically halfway through the molecule, which would split the molecule into mirror images of each other. So if I imagine a mirror here in the middle, notice how the left-hand side of the molecule is a mirror image of the right-hand side. So that's called a mirror plane of symmetry. Okay, so this is the internal plane of symmetry. This is a mirror plane of symmetry. Okay, and now this is exactly true for like objects. So when we considered safety glasses before, and this safety glass was achiral, and the reason is because there is a mirror plane of symmetry. If you imagine a mirror through the middle, then the left-hand side is the mirror image of the right-hand side. So there is a plane of symmetry within the molecule, and that would make the molecule achiral. Okay, so that's an introduction to chirality, what a chiral molecule is, what is an achiral molecule or an object, what's a chiral center, and what are the chances, or when do we see a chiral nature in molecules or objects, even though they have chiral centers in them. Okay, so that's like an introduction to chirality as it relates to stereoisomerism. We will discuss more about enantiomers and mirror images and how to differentiate these in the upcoming videos. Bye.